Hello again, time for physics. This is video lecture 21.2, and we're going to focus in this video on the core content of chapter 21, which is in section 1, where we're going to learn about the mathematical form of what is called Coulomb's law. Coulomb's law is the name given to the formula for calculating what's called the electrostatic force that one charged particle exerts on another charged particle. So the key idea we're going to talk about is the electrostatic force between two point particles, each with some amount of electric charge. So first, let's be clear on what we mean by a charged point particle, or just particle. We mean this in practical terms. A charged particle, or point particle, is any object with electric charge whose physical size is much less than the distance to the neighboring objects. So what I've got down here below are some representations of two charged point particles. Let's focus first over here on the picture on the left. The charged point particles are represented by what look like little orange spheres. The point being that their physical size is small compared to how far apart they are from each other. When their physical size is small compared to how far apart they are, we can treat each object as what we would call a point particle. Okay, and in this picture here on the left, particle 1 is this one, and particle 2 is this one. Particle 1 has an amount of electric charge we'll denote Q1. Particle 2 has an amount of electric charge that will denote Q2. And the actual distance between the two charges is denoted little r. And we've drawn, for visual reference, just a straight line going through the two particles. And in this picture, each particle is positively charged. So they put a plus sign on each little sphere, like that. And what they're telling you there is each particle has positive charge. Q1 for particle 1, Q2 for particle 2. Each of those would be some number, positive number in coulombs. Okay, that's the setup. We have 2-point particles, each has positive charge. Experiments show, everything we're talking about here is based on experiments. Experiments show that there will be a force on particle 1 due to particle 2. And because those two particles are like charges, both positive, the force on 1 due to 2 is repulsive. Repulsive means away from. So we're going to draw the arrow here for the force on 1 due to 2. We're going to anchor this arrow on particle 1. We're going to always put the force vectors anchored on the particle they're acting on. Okay? So we're going to draw this force arrow with its anchor, its tail, on particle 1. And since it's a repulsive force, this force will be away from 2 along this joining line. So it will be this arrow that they've drawn right here. Okay? And we're going to denote that force F12, force on 1 due to 2. Okay, force on 1 due to 2. Now, is there a force on 2 due to 1? I think so. If there's a force on 1 due to 2, there's a force on 2 due to 1. How do you think those two forces compare or relate to each other? Force on 1 due to 2, which I've drawn, and then force on 2 due to 1, which I haven't drawn. Did you say they're equal and opposite? And do you know the reason? Did you say Newton's third law? Okay, force on 1 due to 2, force on 2 due to 1. Equal magnitudes, opposite directions. So if I draw the force on 2 due to 1, I will draw an arrow anchored on 2, and since they're like charges, it's repulsive, so it will point away from 1. So it will be over there like that. And we would label it F2, 1. F1, 2, F2, 1. Equal magnitudes, opposite directions. Now there is one other arrow in this drawing that I want to point out, and I'm getting a lot of stuff already here, so let me start erasing some things. That's enough. Okay. There's another little arrow here that I want to point out because it gives people a hard time. It's just drawn over here to the side. The key thing about this arrow is its direction and its label. It's labeled R with a hat on top. Do you remember what the hat means? It means you're dealing with a special kind of vector called a unit vector. And remember the properties of a unit vector. It's got a magnitude of 1 with no units. It's just magnitude 1. And it has one job in life, to point in an assigned direction. In this case, its job is to point in the direction of the line joining the particles and away from 2. And it's just drawn over here to the side. Okay? If you like, from 2 to 1, because you could draw it wherever you want. You could draw it right there. Okay? Away from 2, right, towards 1. You could think of it that way if you want. They've just drawn it over here to the side here. Okay? Don't get caught up on where it's drawn. Get caught up on the direction it points in. Okay? It points along the line connecting 2 to 1, away from 2 and towards 1. Once that's stated, that sets its direction. Then you can draw it wherever you want. Okay, that's just to help us get a direction, as we'll see, because the force has a direction. But I want to look at these other pictures, as we get more practice. Now I want to focus on the middle picture right here. Now again, we have the particles 1 and 2, with Q1 for the charge of 1 and Q2 for the charge of 2. But now, it may be hard for you to see, but Q1 has a negative charge. They denote that by putting a little minus sign on its sphere. And Q2 has a negative charge. So they're both negative. So when they draw the force on 1 due to 2, they first of all draw it anchored on 1, and they show it pointing away from 2. Do you see why? Force on 1 due to 2. Because like charges repel, and the force on 1 is away from 2. I just want these pictures to be clear for right now. Same R hat direction, because it's the same. It's still 2 particles along the same line. All right, now let's look at this picture right here. Now, particle 1, we're told here, has positive charge, and particle 2 has negative charge. So now they have opposite signs of charge. One's positive, one's negative. So we want to draw the force on 1 due to 2. Now you see the arrow? You see why it's drawn that way? It's drawn that way. This would be force on 1 due to 2. It's anchored on 1, but it points towards 2 because opposite types of charge attract. And then the last picture shows particle 1 is negative and particle 2 is positive. Now sketch the force on 1 due to 2. Again, it's attractive. Right? So we draw it we draw the arrow anchored on 1 and pointing towards 2. Okay? All right, so that's our first little, just with pictures, discussion of this electrostatic force that one charged particle exerts on another. And one of the key things we have to get used to is just dealing with the geometry that's involved and the fact that we're dealing with forces which are vectors. So we got to deal with magnitudes and directions. So what I want to do next is look at a Wiley Plus animation, which is right here. And I want to talk a little bit about what that shows. Okay, so let me get that visible. So it shows two charged particles, 1 and 2, with charge Q1 and charge Q2. And they're given up there, they're set, those charge amounts, by those little sliders at the top. Notice the units are microcoulomb. That's a pretty common unit. 1 coulomb turns out to be a large amount of charge. What's more common are milli or micro or maybe even nanocoulomb amounts of charge. Okay, so these two charge amounts are both in microcoulombs. Particle 1's charge is -1 microcoulombs, and particle 2's charge is +1 microcoulombs. And you can see where they're located because they're represented by disks, and they're labeled Q1 and Q2. And I can move them around with this animation. So I'm actually, just to make things a little bit easier, I'm going to move particle 2 to the origin, as close as I can get, roughly, by eye. Okay? I just put particle 2 at the origin. I didn't even move particle 1. And I want to discuss all the various distances and arrows in this drawing because it's really important. First, the blue arrow that points from 2 to 1 has a magnitude that we'll just denote R. That's just the distance between them, okay? Now, there's R hat. Do you see it? It's this one right there. That black arrow that happens to be drawn with its tail anchored on 1. You could draw it anywhere. But the point is that it is pointing along the line from 2 to 1. Away from 2 and towards 1 if you put it in the middle area. And then here comes the key one. This little kind of purple arrow right there. I gotta make sure I highlight it. There it is. That's the force on 1 due to 2. Notice how it's labeled, F12. Do you see why it's pointing the way it does? This purple arrow? First of all, it's anchored on 1 because it's the force on 1. And it points towards 2 because the particles have opposite signs of charge and opposites attract. Okay? All right, now I want to ask the question. I want you to predict first before I do it. I'm going to change the charge on particle 1 to +1 microcoulombs. How do you think the picture is going to change? That's the only thing I'm going to change. Q1 is going to change from -1 microcoulomb to +1 microcoulomb. How will the picture, the animation, change? Okay. Ready? Have you made a prediction? Let me enter +1, just enter 1, enter. Okay, now both charges are positive. Notice the distance between them, the length of the blue arrow, that didn't change. R hat didn't change because the angle of the line connecting them didn't change. But the force arrow changed. There's now F, if I can highlight it, there it is, F12. It's anchored on 1, but it points away from 2 along their line because they're both positive and like charges repel. All right, here's another question to pose. I want you to make a prediction first before I do it. How will the picture change if I move particle 1 closer to particle 2? I'll try to keep it along that line and just move 1 closer to 2. How will the picture change? Okay, did you make a prediction? All right, let's see. Let me just move 1 along that line closer to 2. Okay? Well, let's say that. Well, the length of the blue arrow got shorter because the distance between them became less. Did you see what happened to the force, F12? That arrow? Did you observe that that arrow got longer? The force magnitude is bigger. The force is bigger. That's telling us, it's empirical evidence, that the force on 1 due to 2 depends upon how far apart they are. And the closer they are, the bigger the force. Or conversely, the farther they are from each other, the weaker, the smaller the force. This happens to be true, that the electrostatic force between charged particles depends upon the distance between them. We're going to have to be able to write this down in a formula, but we can see it's going to have to depend on the distance. Inversely, somehow, on the distance, because as the distance between them becomes smaller, the force magnitude becomes larger. All right, now I'm going to move Q1 onto the x-axis, leave Q2 at the origin. Now how will the picture change? Again, make a prediction, and now just move it down onto the x-axis, as close as I can get. Okay? Now the line between them is right along the x-axis, so now there's the r hat, happens to point in the plus x direction, and then there's F12, anchored on 1, pointing away from 2. In this case, that puts it pointing straight out in the plus x direction. All right, now let's move Q2 away from the origin. Let's move it into quadrant 1 of the xy plane. Predict how the picture will change. Okay, I'm going to move particle 2 away from the origin into quadrant 1. Like that. I'll move it back a little bit so you can see. All right? All right, now we've got a lot of arrows. This blue arrow right here is an important one that points from 2 to 1. That magnitude is the distance between the particles. There's the r hat. It points along that line connecting 2 to 1, okay, and away from 2. Okay, I think we've lost. Okay, I had a technical glitch that I had to solve, but I'm back. So I'm looking at this picture some more. Put this up a little bit so you can see it better. Okay. With this blue arrow right here is the important one for the distance between them. 1 and 2. There's the r hat that points along the line connecting 2 to 1 and away from 2. Okay. If you put it in the middle region. And then they both have positive charge, so the force on 1 due to 2 is repulsive. So the arrow is drawn, anchored on 1, and pointing directly away from 2, like that. All right, so here's the bottom line. We need to be able to, given the amount of Q1 and Q2, and telling you where they are, Q1 and Q2 are located, anywhere in the xy plane, calculate the electrostatic force on 1 due to 2, or on 2 due to 1. That's what we have to be able to do now, okay? All right, so now we're back to my OneNote slides, and I want to write down for you now the famous expression known as Coulomb's law. That is the mathematical formula for the electrostatic force on particle 1, which your author calls the test particle, due to particle 2. Like the little drawing I have below. Particle, it's hard to see, so I'll do some more drawing here. Particle 2 with charge Q2 happens to be at the origin. And particle 1 with charge Q1 is up here in the first quadrant. Happens to be at x equals 4 meters, y equals 3 meters. Q1 and Q2. What's the formula for the force on 1 due to 2? Okay, I'm going to tell you that mathematical form now. The equation is known as Coulomb's law because Coulomb did a lot of the key measurements. And it's a vector formula because force is a vector. F12 arrow, the force, electrostatic force, on 1 due to 2. Okay, here are the key things about it. It depends on the product of those two charge amounts in coulombs, Q1 times Q2. It depends inversely on the distance squared between the particles. Note, that's distance squared between the particles. That's right there. And then the r hat is that little pointing unit vector to help us get the direction right. Remember, the direction is going to be along the line connecting the particles. and either repulsive or attractive, depending upon whether they have like charge or opposite types of charge. And then there is just a proportionality constant right there, denoted right now with the symbol K. K just stands for a constant. Okay? You can think of that as a proportionality constant. That K, and I'll give you the value of it. It's a constant in a moment. Very famous formula, and very important to us for many chapters yet to come. We need to be able to calculate the electrostatic force that one charged particle exerts on another, no matter where those particles are located. Okay? All right. Now let me emphasize that this result comes from experiment. Okay? Very careful measurements were done to get this mathematical form. Okay? Look at this picture below, right below there, and there are the two particles, Q1 and Q2. And it just so happens that they have opposite types of charge. One's positive and one's negative. R is the distance between them, straight line distance. R hat is drawn up here. It's along the line connecting them and away from 2. And then the force is attractive. Force on 1 due to 2. So it's anchored on 1 and it points towards 2. That's F12. Okay? Now, the picture also shows, because we're going to have to deal with this, that this force on 1 due to 2 has components, an x component and a y component. So we need to be able to draw the component triangle with F12, and then its 2 components, x and y. So we need to be able to do that. So I'll do it right here. I'll go to the left. That's the x component of F12. And then I'll go down. That's the y component. Okay, let me clear up some of this stuff so it's a little bit less cluttered. There we have the components. I'll highlight them as I state them. That one is F12x. That's how I would denote it. F12x. That stands for the x component of the vector F12. And now I'll highlight the y component of F12. It's that one right there. And I will denote that one F12y, which means the y component of F12. And we have to be able to find those components, right? Because when we deal with vectors, when it comes down to working with them, we have to work with the components. Okay, so let's move on for right now to the tips at the bottom of the screen here. Again, I emphasize, and I will many times, emphasize that this is a vector equation representing both a magnitude and a direction of the force F12. So first, let's discuss how you could calculate just the magnitude part, if that's what you're interested in. Just the magnitude part of this force. First, the notation. F12 arrow, absolute value. By that notation, we mean we're just talking about the magnitude of the force 12. And of course, just take Coulomb's law. Drop the r hat, the magnitude of r hat is 1. Put magnitudes on Q1 and Q2 because they could be positive, it could be negative. We don't want that. Multiply by k, that proportionality constant, divide by r squared. Then you're sure to have an expression on the right that has no direction and is positive. And that's the formula you would use to calculate the magnitude of the electrostatic force on 1 due to 2. It's also the magnitude of the electrostatic force on 2 due to 1 by Newton's third law. Now what about the direction of the force? That's important too. Force on 1, remember, on 1. If Q1 and Q2 have the same sign, the force is repulsive. That will mean the force is in the plus r hat direction. If Q1 and Q2 have opposite signs, the force will be attractive, and the force will be in the negative r hat direction. That's what my drawing up above shows. It shows the force on 1 is attractive, so the force is pointing towards 2, which is opposite to the r hat direction. All right, we're going to spend a lot of time practicing with getting the direction and magnitude and the direction and the components of the electrostatic force. Okay. All right, let me tell you next, however, what you can learn by experiment about the value of that proportionality constant, little k, in Coulomb's law. Okay? I'm just going to tell you its value in SI units because it's determined by experiment. There's no way to predict what it would be. You have to measure it. I'm going to tell you its value and its units in the SI system, and then explain briefly why those units are the way they are. First, the value of this proportionality constant k. 8.99 times 10 to the 9. Okay? All right. Now let me talk through what the units are and why they are what they are. Let me write down the formula for the magnitude of F12 using Coulomb's law. K, magnitude Q1 times magnitude Q2 over r squared. And now let's talk about the units of all those quantities. On the left, we have the magnitude of a force, so it has to be in newtons. What do we have on the right? Give myself some room here. I have a charge amount, so that's got to be in coulombs, C, multiplied by another charge amount, so that's in coulombs, C. So those two together, Coulomb squared. And then I have a distance squared in the denominator, so that's meters squared. So for the units of the constant k, I've given you the number, but what are the units? The units of k have to be such that k times q1 times q2 over r squared has units of meters, newtons, because it's got to represent a force. So the units of k have to be Newton times meter squared over Coulomb squared. So that when we multiply by Q1, Q2, the per Coulomb squareds and the Coulomb squareds cancel, and we divide by r squareds, the meter squared and the meter squared cancel, and we have newtons. So that's why the units of this constant, this electrostatic constant, little k, are Newton times meter squared over Coulomb squared. You can just take that to be a measured constant in Coulomb's law. Now, the next thing you just have to trust me is something that's useful to do, because on the surface of it, it's not immediately obvious why you would need to do this. Let's write this constant k as a combination of some other constants, including pi. Okay? Let's write k equals 1 over 4 times pi times a new constant that we're going to denote by the symbol epsilon subscript 0, like that. In fact, most physicists call it epsilon 0, although it's not its actual name, but actually most do, epsilon 0. You could certainly make that definition. Okay, I'm going to just say k equals 1 over 4 pi epsilon 0, and given that you know what k is, you can solve for what the constant epsilon 0 would have to be. Here's what you get. The value of this new constant epsilon 0 is 8.85 times 10 to the minus 12 Coulomb squared over Newton meter squared. And you want to know its actual name, it's called, although that name doesn't tell you much, the permittivity constant. If we use that notation introducing that new constant epsilon zero, the permittivity constant, here's the new version of Coulomb's law, the version that I would say most physicists would use, right here. The electrostatic force on 1 due to 2, F12 arrow, is Q1 times Q2 over 4 pi epsilon 0 r squared, all times r hat. Okay? All right, that's what we have to practice with for the rest of this chapter. And in fact, let me go and do a little bit of practicing with you right now with this static picture from the Wiley Plus animation with Q1 and Q2. Q2 at the origin, down here. Q1 up at x equals 4 meters, y equals 3, with charge Q1. And Q1 is -1 microcoulombs. Q2 is +1 microcoulombs. To be clear, the coordinates of our particles, x1, y1, are 4 meters, 3 meters, and x2, y2 is 0, 0. That's the origin. Our first task is to calculate the magnitude of the force on 1 due to 2. We need to be able to use Coulomb's law to do that. Okay? Magnitude of force on 1 due to 2. That will be K times the magnitude of Q1, because I don't want any negatives, times Q2, it's already positive, over r squared. R, remember, is the distance, straight line distance, between the two particles. Okay? All right, let's plug in numbers. We'll use the value of K, 8.99 times 10 to the 9 Newton meters squared over Coulomb squared. The absolute value of Q1, 1 times 10 to the -6 coulombs, right? Microcoulombs. Q2, 1 times 10 to the -6 coulombs over r squared. What is this distance right there squared? Well, remember, I know that is 4 meters along there, along x, and that along y is 3. So I think Pythagoras would enable me to get r squared, wouldn't it? It will be 4 meters squared plus 3 meters squared. Notice it's r squared, not r. And you can put those numbers in your calculators. You need to be able to do that. And you will get, note that Coulomb squared downstairs cancels those 2 coulombs upstairs. I'll have a meter squared downstairs and a meter squared upstairs. So I'm going to be left with a unit on the right of Newton, which I have to get. And if I put all those numbers very carefully into my calculator, I'll give you 3 digits. 3.596 times 10 to the -4 newtons. And that's the magnitude of the electrostatic force on 1 due to 2. But now I also want to calculate the x and y components of that force. There's the x component right there. There's the y component. Or if I just come down here below and draw the force triangle, F12 is going down and to the left. There's F12x component, and there's F12y component. Notice their directions on those arrows. Left for the x and down for the y. Let me also, in this little component triangle, label that angle up there theta. All right, next question. I'm going to need to know that theta. because I got to get those components, and I need theta in that triangle, right? So what is theta? They don't tell me outright. So let's go back up here, and let me simplify the drawing a little bit, okay? And what I contend is that the theta that I drew down here in my force component triangle is the same as that angle right there, which is the same as that angle right down there. You see that? Got to be able to see that. So that one way to get theta that I need is by using this larger triangle down below and get this theta right here. Because that's the theta I'm talking about. And for that, you can just observe, I hope, that tan theta, opposite over adjacent, is 3 meters over 4 meters, where the meters cancel. So that theta is the inverse tangent of 3/4, which, giving you 3 digits, is 36.87 degrees. Okay, now that I know theta, go back to the force component triangle, and let's calculate the components. Let's calculate first F12 x component. Okay, put that what I want here so that it's clear what I'm wanting to calculate. Okay, the component shaded in yellow there, F12x. Now you have to remember all we learned last semester about finding components of vectors, because those rules have not changed. And what you've got to realize here, this is the way I'm going to do it, is that little component arrow points to the left. The left is negative x, so this component is negative. I've got to put that negative in by hand. And that x component is adjacent to the angle theta. So I take cosine theta and I multiply by the hypotenuse. Magnitude of F12, right? Because it's a force triangle. So I take the magnitude of F12 times the cosine of theta with a negative sign. It's negative. Now the magnitude of F12, 3.596 times 10 to the minus 4 newtons, times the cosine of 36.87 degrees. And for the x component of the force, I get, now I'll give 3 sig figs, negative 2.88 times 10 to the minus 4 newtons. And now how would you find F12 y component? So now, see if I can get rid of. Now let me shade the component I'm talking about. It's that one right there, which points down. So I have to realize that that means F12y is also negative, and I have to put that in by hand. And that side is opposite to theta. So I'm going to take sine theta and multiply it by the hypotenuse, which is magnitude of F12. So I take negative 3.596 times 10 to the minus 4 newtons times the sine of 36.87, and I get negative 2.16 times 10 to the minus 4 newtons. So this is the kind of thing we have to be able to do. We give you 2 particles. They could be located anywhere. We'll tell you where they are. We'll tell you how much charge they have each, and you will need to calculate the force between them. Let's say on 1 due to 2. And a common way we'll do that is first get the magnitude of the force on 1 due to 2, and then get the x component and the y component. Practice, 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 because that's what we have to be able to do over and over. Now let me go back one more, because I want to bring on one more topic before we end this video. It's very common that we're going to have to deal with more than 2 charged particles at a time. 3, 4, 5, who knows, but more than 2. How do we do it? Well, first you have to learn from experiment how, but I will tell you. So now we're dealing with multiple charged particles, meaning more than 2. How do you calculate the net electrostatic force on a charged particle due to two or more other charged particles? Here's the procedure, very important. First, clearly identify that chosen particle and then find the force on it due to each of the other two. So let me look at this picture over here in the lower right corner. It shows three particles and an XY coordinate system. X-axis to the right, Y-axis upward, and I'm going to number the particles. Particle 1 is the one on the Y-axis, and it has a charge that I will just label Q1, but the picture shows, it may be hard to see, that it's positive. It's got a little plus sign by it. Okay, let's say the particle down here on the left is particle 2, and it's got a charge Q2, and it's positive. And then the charge over here is particle 3, and it has a charge Q3. And let's just say, for the sake of argument here, that the Q's are all equal. Q1 equals Q2 equals Q3. And that what we want to find is the net electrostatic force on 1. Let's just sketch it in the drawing. Okay? All right, let me get rid of that Y there. What do we do? All right, so we've clearly identified the chosen particle, particle 1. And we're going to find the force on it due to each of the other two. So there's going to be a force on 1 due to 2, and a force on 1 due to 3. We'd have to find those. In this little scenario, I'm going to draw them, sketch them. It says here, draw those force vectors in a free body diagram of the chosen particle, with the tails anchored on the particle. So if I want the net force on particle 1, I want forces on 1, I'm going to draw my arrows anchored on 1. So here we go. Let me draw a little line connecting 1 and 2 for reference. I'll make it a dashed line. And a line connecting 1 and 3 for reference. I'll make it a dashed line. All right, so how would you sketch the force on 1 due to 2? Take a moment, think about it. Pause the video if you need to. How would you draw the arrow representing F12, force on 1 due to 2? Okay, did you say that it would look like this? Anchored, the arrow's anchored on 1 and points directly away from 2, along the line connecting them. Do you see how I know that? Because 1 and 2 are both positive and like charges repel, and the force has got to be along the line connecting the two. Now that's just the force on 1 due to 2. And if I told you the value of Q1 and the value of Q2 and where they were actually located on their axes, you could find the magnitude of that force and its X and Y components. You should be able to. Now there'll be a force on 1 due to 3. I want you to sketch that one too. Do it first on your own, please. Pause the video, do it carefully, and then come back. Okay, so sketching the force on 1 due to 3. Did you draw an arrow anchored on 1, but pointing away from 3? Like that. And then label it, force on 1 due to 3. And again, if I tell you Q1 and Q3, and where 1 is located and 3 is located, you can find that magnitude of F13 and its X and Y components. And then there's one more step. Add all those forces as vectors according to the rules of vector addition that we studied in Chapter 3. Vector addition. You can't just add, please note, you cannot just add up the magnitudes of F12 and F13. Because that's not how you add vectors like you see here, where they don't point in the same direction. The result of that vector addition is the net force on particle 1. Now, if F12 and F13 have the same magnitude, then when you add them, I'll sketch the sum by vector addition, it points straight up the y-axis if the vectors have equal magnitude. And that's your F net 1 right there. That's the process for finding the net force on a charged particle from two or more other particles. If you want to know the fancy word for what we did, it's called the principle of superposition. And superposition is a fancy way to say add. Okay, so that's the background. We're going to have our class video in a minute where we're going to practice, or later, where we're going to practice with Coulomb's law. But now let me leave you with a class engagement exercise for Blackboard. And it's all about practicing with Coulomb's law. Going to be lots of practice. Here we go. See the figure? It shows four particles that are fixed in place. Particle 1 is this one. Particle 2 is this one. Particle 4 is this one. Those particles all have the same positive charge, which is denoted by the amount plus big Q. Okay? So 1, 2, and 4 all have charge plus big Q. Particle 3 is the one up here on the y-axis. Okay? And it has charge negative big Q. So just the opposite of the others. The picture also shows the net force, F4 net, acting on particle 4, which is the one at the origin, and it shows that it's in the positive direction of the y-axis. There it is, anchored on 4, because it's the net force on 4. Notice it points in the plus y direction, given that 1, 2, and 4 have charge plus big Q, and 3 has charge negative big Q. The first thing you should do, although this is an actual part of the exercise, is convince yourself how F4 net points the way it does in this drawing. Draw on 4, F1 4, F2 4, and F3 4, and convince yourself how, by vector addition, F net 4 points in the direction of this arrow that you see. That's important to understand that before you start the actual exercise, okay? Okay, now, here come the questions for the exercise. We are going to be allowed to move, one by one, particles 1, 2, and 3. 1, 2, and 3. And we're going to move them in the ways listed below in A through F. And for each way that we're going to move a particle, you need to determine how the direction of the net force vector on 4 will be affected when we make the move. And the possible answers are that F4 net will rotate clockwise, that way. F4 net will rotate counterclockwise, that way. Or F4 net will not rotate at all. It's one of those three. F4 net will rotate clockwise, counterclockwise, or not rotate at all. And then here are the 6 cases, A through F. In case A, all you do is move particle 3 closer to the origin. That's all you do. How is F4 net affected? Case B, move particle 3 away from the origin. How is F4 net affected? Case C, move particle 1 closer to the origin. How is F4 net affected? Case D, move particle 1 away from the origin. How is F4 net affected? Case E, move particle 2 closer to the origin. What's the effect on F4 net? And finally, case F, move particle 2 away from the origin. What's the effect on F4 net? Okay? So those are the questions you answer on Blackboard. Okay? All right. There'll be more practice then in the upcoming class video, but that's all for this video.